screen now?
Yes.
Okay.
We can see a map somewhere in the background.
Okay. So, good afternoon, everyone. So, I am studying at King Mongkut University, and my name is Premyuda Dechboon. My my advisor is Professor Poom Kam-im. So, I would like to present my work in the topic of an inertial projection like method for solving a generalized Nash equilibrium problem. So, one truth, this is my content today. First, I want to talk about one truth in our world is that many competition are all allow us, and in such activities, or someone know it as business, people want to gain more and more benefits. In other words, we can say that people want to decrease their own loss as much as possible. So we want to study that kind of scenario. So we want to find one thing, we call it equilibrium point. In such situation, we can recall it in mathematics. That is, we consider it as game. So in the game, we need some component which consists of player. In the game situation, we need at least 2 players. The next one that we require is that the set of all possible outcomes that in other words, we call it strategy set. Like xi is the strategy set for the player I. So the next one is the loss function. So fi is the loss function of each player. When we consider the loss function of each player, meaning that all of the strategy set of all players need to consider as well. So we consider the set X, which is the product of all xi, that is strategy set for each player. And the mapping fi will be mapped to the real number. So that we can, another example is that some other business, so that we can write it in the mathematical way. That is, John Nash give us some definition of the definition of Nash equilibrium point. Okay, just a moment, please. Okay, so in the n-person non-cooperative game is that we consider the strategy set xi, which is non-empty set, and for the n player, for example, player I is player 1, player 2, or player n, and we can say that x bar is the Nash equilibrium point if x bar is n tuple point like this, which it is satisfy this problem, that is minimize fi, which is loss function for all player. Oh, sorry, this one should has this one. Okay, when at the I component, it is subject to the set strategy set xi. And Nash equilibrium point concept, meaning that if it is Nash equilibrium point, so that no player can gain more benefit if they change their strategy set. We can see that the previous concept is written as the minimization problem. So this is when we consider the closed and convex set, and the function h is convex, so that we can have the convex optimization problem. And we know that there is some relation between convex optimization problem and variational inequality problem. That's why in this work, we consider the variational inequality problem. Okay. So from the minimization problem, we can write it by using minimum principle as this one. So we can consider this kind of function in the quasi-variational inequality problem when we set x is product of xi. So this capital F is replaced by this one. Okay. And another way we can say that if x bar is Nash equilibrium point, then it satisfies the minimization problem. And also we can consider, I'm sorry, yeah. So we can consider y, the vector y as the n tuple, but at the I component we change to be y. So we can have that. In other words, is whole in case of x bar is variational, is satisfy variational inequality problem. So we can conclude that the x bar is a solution of Nash equilibrium problem if and only if it is also a solution of vector inequality problem. So from the concept of Nash equilibrium problem, we can see that this one, let me recall this one. We can see that this stability set is fixed for all pairs, right? So in case that we change the stability set to be varies, meaning that it depends on other players' stability. So we consider the set value mapping Ki, which is mapped from others players' stability to his or herself stability set. So we can study the extension version of Nash equilibrium problem, known as generalized Nash equilibrium problem. That is, we write it in the minimization problem, but at the I component, it depends on the set value mapping Ki. So this one is okay. For example, when we have the minimization problem like this and this, we can write the set value mapping K, which is flexible set, by this one. You can see that Ki is the stability set of the player one, which is depends on the stability of player two, which is B, and also stability set of player two depends on the stability of player one, which is A, this one. From this concept, we also consider quasi-variational inequality problem. That is, we change this set to be the set value mapping, where we set the set value mapping K equal to the product of all stability set Ki. Okay. And in this work, we consider the real Banach space H, which K is a closed convex subset in Hilbert space H, and the projection that we use is orthogonal projection, which is considered as this definition. And this one is normal property, usual property from the projection. In 2010, Professor Chang introduced some projection-like method. Okay, we will call this one shortly algorithm A. Okay, from this algorithm, we would like to consider this one with the concept that we know some initial type algorithm which first introduced by Professor Poyak, and we know that in this method it can help us to speed the convergence sequence of that algorithm in case that algorithm is provide two steps. So the algorithm look like this one. Also in 2020, Chen Hu exhibits strong convergent result in the initial projection type method in the real Hilbert space given by this one. So from the three algorithm, we propose new algorithm with the initial step. So in my work, I need some definition that is let X be a subset from Hilbert space, and we consider F be a mapping from cell mapping from X. So we can say that F the mapping F, capital F, is pseudo-monotone if for any xy we have this inequality, which imply that this inequality hold also, and monotone on X if this inequality hold. Okay. And at the point X, we can say that it is monotone at point X if this inequality hold, and strictly monotone if this inequality hold whenever X is not equal to Y. The next definition is about continuity. So the set value mapping K is said to be weakly upper semi-continuous at x0 if for any sequence from X, it is weak converged to x0, and for any sequence Y from set value mapping K, which depends on xk, yk converge weakly to y0, and it's implied y0 is in the kx0. For the lower semi-continuous, for the weakly lower semi-continuous, we have that this one is almost the same, but if we have this one, it implies that for each y0 in the kx0, there exists sequence yk from the kxk such that yk converge to y0. And we can say that this set value mapping k is weakly continuous at x0 if it is both weakly upper and lower semi-continuous at x0. Moreover, it is weakly continuous on X if it is weakly continuous at X for any X in the set X. From these two definitions, and actually there are many basic. Okay. So in main result, we suppose we let first that this set S star be the set that is the set of all X in the intersection of Kx, such that this inequality hold for any Y in the union of Kx, and we assume for assumption that is S star is non-empty, F is pseudo-monotone on X, and X is in Kx for any X. And the last one is that K is weakly continuous on X. Moreover, we denote some notation that is, I can say, an error, so that this one is an error. Then we propose our algorithm that is we give some constant here, and then the first step of the initial step is that we consider Wk divided by this one when this gamma k is depends on this force. After that, we consider Ck, that is projection of Wk minus f of Wk, and then we take y equal to this one with line search, with this line search. And then we got the xk plus 1 from this one, and we do it again and stop when the error is less than something, okay, less than some value. And our result, we got that our algorithm is verified in case that verified, okay. And after that, we prove that our sequence generated by algorithm 1 is bounded. After that, we show that any accumulation point of the sequence xk generated by algorithm 1 is the solution of quasi-equilibrium problem. And then we have shown that if f is strictly monotone and accumulation point at the accumulation point x tilde of xk, then the sequence converges strictly to x tilde. By the way, we will show that the next one is our example, and in our example is in n-dimensional of real number, so that we will get the strong convergence in our example. So in our example, we consider the game such that there are two players and each player can pick the number between 0 and 10. So when the first player pick, another one need to pick, but the sum of two numbers must less than or equal to 15. So we can write, we given the cost function like this, and then we can write the set value mapping of their strategy set like this. Okay, we can see that if we consider the gradient of two functions, this one, we can get the capital F like this as we derive the problem at first. And our algorithm compare with Professor Chang, that is algorithm A, we can see that our algorithm is faster in case of we consider CPU time and also have less number of iteration also. Okay, thank you very much for your listening and suggestion.
Thank you too. Very nice presentation. So, if any comments, questions, or remarks,